My name is Pascal Poupart, so I'll be the host here for this talk, and it's my great pleasure to introduce Matthew Taylor. So Matt is a professor at the University of Alberta, and he's also a fellow with AMII, so the Alberta Institute for Machine Intelligence. So Matt has been working on reinforcement learning in multi-agent systems since 2003. So he's got definitely, a breadth of knowledge and a depth of knowledge that didn't just start with deep reinforcement learning, but goes back many years before that. And therefore, is an expert with respect to the foundations as well. So at the University of Alberta, he directs the Intelligent Robot Learning Lab. And as I mentioned before, he's also a fellow at AMII. So in fact, a fellow in residence at AMII. He's his current research and fundamental research for reinforcement learning includes human-in-the-loop AI, multi-agent systems, and robotics. And then his applied research interests revolve around getting cutting-edge machine learning and AI out of academic labs and into the hands of companies. And here it's interesting. He tells me that he focuses most on companies whose names don't start with the letters FAANG. So I'll just leave it at that. But I guess I understand that Matt likes to make sure that the research is democratically used by everyone. Okay, so without any further ado, so we'll let Matt start, and then the title of his talk is Leveraging External Knowledge for Reinforcement Learning, How to Cheat and Still Feel Good About It.
Awesome. Thanks, Pascal. And I do a bunch of stuff in robotics and multi-agent learning, and that's what I'm not talking about today, but I'm always happy to talk about that later. I tried to come up with a kind of provocative title because I want to talk about cheating. So a lot of reinforcement learning is the real core AI technique of letting your agent learn everything from scratch on its own. And I'm going to argue in many cases that could be impractical. And instead, we should be using our background knowledge. We should be cheating as much as we can in order to make reinforcement learning even more practical. So I have 4 parts of my talk. The most important part of this slide is I really would like you to ask questions. I've got the Zoom chat open. So if you want to drop in questions in text, that's great. If you want to unmute and yell out things, that's awesome too. This will be much more exciting if it's not just Matt talking to the screen. So please do. One person said we might come in hot with questions. Awesome. Let's do it. So first, very quick background on reinforcement learning to make sure we're all on the same wavelength. We have an agent that interacts with an environment. The agent is in some state. It can take an action and then gets a reward. So it's unlike supervised learning, it's never told what is right or wrong. Instead, it's got to interact with the environment. And that interaction will probably have some cost. If it's in simulation, it's just compute. If it's in the real world, your robot can wear down. If you are trading stocks, it's going to have a real cost in terms of money. So generally, we want to learn fast. Reinforcement learning has been around for a long time, but it's recently gotten really popular because of some really impressive successes. So things like Go and Dota and StarCraft 2, but it's not just video games. And this is one of the things that I really enjoy talking with companies about, that look, it's not just game playing. We also see practical data center cooling. We see it used in robotics. There was some cool work on pricing American options. And I was lucky enough at Borealis AI that I got to work a little bit on stock trading. So it's fun to be able to point at a deployed RL agent that's actually doing stuff. That's pretty cool. Now, I'm an RL person. RL is amazing. It's not always perfect. So where is it imperfect? Well, for one thing, in this Dota work, they used a few hundred days worth of gameplay every day they trained. They had many servers in parallel, and they're able to use a huge amount of compute. So sometimes you can really require lots of computation and interaction. But let's take a step back. What is the agent doing? Well, it's learning to maximize a reward, and that's going to be what you tell it to do, whether it is what you want, what is ethical, what is legal. So for instance, There's this great example from OpenAI where they had a boat that was supposed to go around this racetrack, and instead the boat was just stuck in a reward circle, and it was just getting points. It wasn't actually winning the game. It realized it could just get a bunch of points and maximize its reward. So when you're talking about RL in the real world, then you need to think about, how do I define that reward function? Is it an iterative process? Is it a one-shot thing? Can I learn an optimal policy for this reward and then figure out how to tweak my reward to make it better? But for this talk, we're just going to assume that we have a reward function given to us. Someone hands us an MDP and we just need to do well. Another problem is solutions that when we learn a policy, how to act in reinforcement learning, that's often black box. And if you want to deploy a policy, it can be very difficult to get someone, when you go to someone and say, hey, use my agent, I can't really explain how it works. That can be a little bit dicey. So that's another thing we as a field and we in my group are working on. And what I was just saying is, you can have very real costs. So if you are trading in the stock market, if you have a robot, even if you're in simulation, there is some cost and you want to learn quickly. When you're in the real world, the initial performance could be very important. If you put your policy on a robot and start learning, and then the robot's actuator breaks, you're going to be in trouble. So figuring out how can I get that good initial performance could be related to safety. Today, I'm going to talk about how we could cheat in order to get that better initial performance. So hopefully that this is all boring. Hopefully you've seen all this before and this is not controversial. But now I'm going to hop into the next step where I talk about how an agent could learn from an agent. And I'm just going to take a real quick drink of water in case anyone wants to drop a question in the chat or unmute. Okay, it sounds like either everyone agrees or everyone's asleep. So I'll go with the first one. So first, let's talk about learning from agents. Well, I got to my first faculty job, 2010, and I'm like, okay, now I get the chance to work on anything I want to. What am I going to do? And I'm not really sure, but eventually I came up with this diagram. And this is kind of what has been driving me over the past 11 years. Thinking about, I've got an agent that robot or virtual agent could learn, but it's not often going to be alone. So you could think of, if I have an agent that wants to learn, it could learn from another agent. Or if I have an agent, it could learn from a human, or even an agent could teach a human. So first, let's talk about how one agent might teach another. Now, the simplest thing you could do, thank you, Graham, is transfer learning. So transfer learning now, sometimes people refer to that as policy distillation. The idea is that you can use one existing RL agent to speed up learning on another one. And this could be even if the agents are not identical. So they might have different state and action spaces. They could have slightly different rewards. You could take an agent in one MDP, bring it to another MDP and learn faster. All of that's fair game. And we could say, well, if I don't have transfer, I've got this blue curve. If I do have transfer, I've got this red curve. So I could say, oh, well, the red curve is higher. So there's more total reward for the red curve. That's cool. You could also say, I've got some threshold performance. So maybe I want to learn a gate where the robot doesn't fall. And I really do want to learn a fast gate after that. But most important is just get the stupid robot to stop falling down. So in that case, if I've got that threshold performance, maybe transfer lets me reach that performance faster. Or there could be a jump start. So I mentioned that initial performance. Maybe you can use transfer to get a better initial performance, or even asymptotic performance. So these are all potential benefits of transfer learning. If you've got a trained RL agent, great. One of the drawbacks of transfer learning is you often need the agent's brains. So if you do not have access to their code, this may not work. If you have an agent that is not an RL agent, if it's not a temporal difference-based agent, so it's a genetic algorithm, maybe it doesn't work as well. One way to get around that is, and I should also mention that if your goal is to learn this very difficult task, we've seen cases where you can learn a set of simpler tasks and learn that final task faster. but you need a carefully designed curriculum. So you need, in general, you need a person. Sometimes you can automatically learn a good curriculum where you pick increasingly difficult tasks. If you're interested in curriculum learning, I happen to know about one paper that I personally like as a nice survey. So I'll just leave that pointer there if you're interested in curriculum learning. But let's assume that we don't have access to the teacher's brains. We don't have access to that because we don't have the right API, it's by another manufacturer, something. In that case, one thing we could do is think about, instead of transfer, let's frame it as teaching. So in particular, you could think of one agent providing action advice. And maybe there's only a limited amount of advice that it can give because advice is costly, or you want to make sure that the student can outperform the teacher because the teacher might not be perfect. And that if the teacher is always saying you must do this, then it's going to be hard for the student to outperform. So now we've got the student that's interacting with an environment, learning a policy. And now we assume also there's a teacher. So this teacher that is experienced, maybe not perfect, but probably better than random at least, is watching the student and can intervene with some action advice. Go up, go down, go left. You could think about the teachers providing much higher level advice, stay away from the ghosts, get the power pills. But for now, let's just think about low level action advice, because that's something that should be relatively easy for one agent to convey to another, even if they're made by different manufacturers. So how could we use this advice? Well, first, let's say how much advice you can use. In this particular paper, we said, I'm going to learn to play Pac-Man. An episode in Pac-Man lasts up to 2,000 steps, and I'm going to only allow 1,000 pieces of advice. So the teacher is allowed to provide less than one entire episode worth of advice. So if the teacher has this small amount of advice it can give, how do you figure out where to use that? Simplest possible thing you could do, just dump it all out at the beginning. Use up that 500 pieces of advice right at the beginning, and then let the agent learn. Okay, that's not a very interesting paper. Let's make it a little more complicated. What if we tried to identify places where the advice could be more useful, more important? So if we had some way of saying, oh, this state is more or less important, at the important states, I could give advice. And at the less important states, don't. Okay, great. I just kicked the can down the road. What do I mean by importance? One thing, and there are many ways of defining this. One way that worked fairly well is a simple heuristic where you look at what's the difference between the best and the worst actions. So in the upper left here, I've got Pac-Man, and if Pac-Man makes the wrong move, he's dead. If he goes right, he's going to die. Whereas if he goes up or left, he's got a chance to continue living. Whereas on the right, I could get this pill, I could get that pill. It doesn't matter a whole lot. So maybe we should focus our advice on places where it's do or die, where if you do the wrong thing, it can make a huge difference. Okay. Two other things you could also think of. Let's say I've been assuming that the teacher is giving information to the student. Let's assume it's two-way. So the student can say, hey, teacher, I'm going to go up. And then the teacher says, no, go right. So the teacher will only correct the student if the announced action the student is going to take is wrong and it's an important state. But ideally, you don't have to have the student keep yelling at the teacher. It's easier if it's just one-way communication. So you could also think of the teacher predicting what the student is going to do. So is the state important? And is the student going to do something stupid? If so, then I will use a piece of my advice. Okay, so we've got these four types of advising, and we found in a bunch of different environments and a bunch of different settings, we get curves, learning curves like this. So we see in blue that we have, this is the agent, how it normally learns. So over time, over the x-axis, it improves its performance. And then we see if we dump out all the advice at the beginning, it initially none of these methods really help a whole lot. But even if I dump all the advice out at the beginning, I'm able to very quickly learn. So I get this nice improvement. If I use importance advising, it gets a little better. If I use mistake correcting or predictive advising, it gets even better still. So this is evidence that being a little tricky about how you allocate this budget, how you let the teacher give action advice to the student, can significantly improve learning. And one of the things I don't show on this graph, excuse me, is that in different cases, the teacher could have a much worse performance than the student's final performance. Because one of the important assumptions I like to make is that the teacher is not perfect. I really do want the student to be able to outperform that teacher. So as long as the better the teacher is, the better off the more quickly you'll learn in general. But even if the teacher is just a little bit better than random, that can still give you a statistically significant boost. So the point of all of this was to say, even if one experienced agent is not perfect, even if it can only give a few pieces of action advice to a student, it can still make a significant improvement in learning. So if you've got an agent sitting around, even if transfer learning isn't applicable, maybe you can get something useful out of it.
So Matt, I have a question here. So in what scenario would a budget be essentially something natural that arises? Because I guess when in the past, when I've done some work on in terms of reinforcement learning with advice, the problem I ran into is that often we have scenarios where really, I guess the teacher, there's a cost to bother it, and essentially, and then so I guess one scenario that is already popular and makes sense is whenever I guess the teacher just produces a demonstration and then we do inverse RL, right? But then if now the student is essentially just acting in an environment as teacher has to oversee, then I'm having trouble coming up with scenarios where as a teacher, I would want to like continuously be monitoring the student. And then on top of that, somehow, I guess there's a budget. The budget seems to count like how many times I would give an advice, but I mean, I'm continuously monitoring, so that's not part of the budget somehow. So yeah, I don't know if you're going to talk more about this, but I thought I'd ask.
No, this is great. So there's a bunch in there to unpack. So one scenario would be you brought the new robot home and you've got the old robot that's supervising it, but you really don't want to be paying for two robots to be running. You really want to retire the old one quickly and just start using the new, more capable one. Another example would be that it's not an agent that's teaching, it's a person. So that person's not going to be willing to sit there forever. But in both of these cases, my assumption was you use some budget, you teach, and then you leave. So at some point, and in this case, relatively quickly, the teacher is just going to say, good luck and Godspeed, and then leave the student alone. But you're right, if you wanted to really be stingy with that budget, then I'm assuming that the teacher could just sit there for a long time without any additional cost. So that could also be factored in.
Okay.
I think there was another part to your question, but I think I forgot it.
Well, anyway, I think that's good. Let's keep going.
Okay, thank you for the question. But this is a great place to catch my breath. Are there other questions about this general teaching setting? Advice?
Yeah, actually, I may have another question. So here, I mean, is it fair to say that your teachers are basically experts and then you put some kind of fixed strategy, heuristic, or policy on how to transfer their knowledge to the learner, but they are not trained to be teacher in some sense?
So good.
Is that
so right. So we
summarize what you have done here?
Yep. So we could a teacher learns well, you could call it an expert, it's fixed. And then this is a heuristic method for how we can exploit that teacher.
Okay.
There's other work that I and others have done where you actually train a teacher that learns how to teach. So if the expert knows beforehand that it's going to have to, it's not just playing Pac-Man, its goal is to be able to teach Pac-Man. That's also something that you can do. Unsurprisingly, If it's a learning approach, it can outperform this heuristic approach. Also, probably unsurprisingly, learning how to teach can be quite data intensive.
Okay, right. Yeah, I guess that's why people go for a Bachelor of Education.
Exactly.
Thanks.
Awesome. This is great. Please do keep asking questions.
Hey, Matthew.
Yep. Awesome.
Sorry for interruption. Another question. So in this slide, you show Sarsa as probably the algorithm you're working with in these settings. So as far as I know, Sarsa is more towards like this tabulate setting. And how do you think this teaching method can be extended to continuous control and continuous observation settings with more complex environment?
Yeah, so in this case, we're using Sarsa with Pac-Man. So it was a continuous state. It was discrete actions though, but you're right. We could also, on the next slide, I talk about how we can also use this in deep reinforcement learning. But it's one of the things I like to argue is that many ideas should be tried out in shallow RL because it's very quick. And then if you want to apply it to cutting edge domains, then drop it into deep RL. But if I just said, hey, I did this in a tabular domain, it wouldn't be nearly as much fun.
Awesome, thanks.
So since I got that question, oh, no, go ahead.
Sorry, Matt. Yeah,
no
while we're on the slide, I actually had a question. So it looks like the performance of predictive advising and mistake correcting are pretty similar. Is that just a coincidence, or is there like an actual reason behind that?
Yeah, this was actually one of the surprises of this work, because I assumed that mistake correcting would be much better, where the student has to tell the teacher what it's going to do. And it turns out in Pac-Man, the teaching agent is able to look at the student and pretty quickly predict reasonably well what the student's going to do, especially at the beginning where it's giving this advice. So since the teacher is able to make these really high quality predictions, it's actually almost indistinguishable from mistake correcting. And that was quite a surprise. Oh, great. There's a question in the chat. Is the advice of an imperfect teacher contingent on confidence? So I am going to postpone this question for a few slides when I talk about teacher confidence. It's like I paid you to ask me that. Awesome. So, okay, so I just was talking about the teacher providing knowledge. The teacher has more information. It makes sense that the teacher would jump in and say when the student should take an action. But you could also argue that the student, if it knew where it was confused, maybe the student should ask for help, actively ask. And that's one thing we did at AAI 2020, where we had a deep RL agent that could proactively say, I'm confused. I have an ensemble and my Q values don't match up. I don't know what I should do next. I'm going to ask the teacher. And in this case, this can work as well. And we showed this in Atari. But there's also some nice work by Ofra Amir out of Microsoft Research, and there's some more recent work out of MIT where you can think of going in both directions simultaneously, where the teacher can provide advice proactively and the student can raise its hand and say, help me out, I'm stuck. But when one direction should be preferred to another direction isn't really known yet. So that's an open area of research. Another open area of research I'll highlight is what if, like Pascal was saying, what if instead of a budget, so how do I say the teacher could give 500 pieces of advice? How did I pick that? What if there's a cost? What if I had to go on Mechanical Turk and say, I'm going to get 5 pieces of advice for 15 cents? How can I reason about that? Well, one way to do this is think about value of information. And you could say, well, we could think about it in a bandit setting to start. So if I'm near the end and I'm not really sure which arm is best, how much would I be willing to pay a teacher to tell me about one particular arm? And that's going to depend on how much time I have left, because in general, the longer amount of time I could exploit that information, the more useful it will be. But calculating the real true value of information can be quite computationally challenging. So you might think about doing something about myopic value of information. So there we're trying to understand exactly how much would I pay for a piece of advice. And this is assuming that the teacher was perfect. What if the teacher is only right 90% of the time? Well, I could factor that into my value of advice. So when we think about getting action advice from a teacher, there is a ton of open questions here. And the teacher, in what I've been talking about, the teacher was a RL agent, but the teacher could also be a human. Or in some cases, it could even be a program. So if I had a program which was doing some task for me, I could have my RL agent asking that program for help. And then once the student outperformed that program, I could just turn that program off and not listen to it anymore. So that's another way that if you have existing knowledge, if you have a way of accomplishing a task, even if it's not perfect, use that knowledge. Don't just throw it out. That's my main argument. So Pascal also said, okay, you've got this robot giving advice. Well, what about humans? Humans might not give action advice. Humans might give demonstrations. Well, there's actually a ton of stuff humans could do. So I want to think about, when I'm thinking about agents and people helping each other, I want to think about something that's suboptimal. And if I'm thinking about humans, well, one thing is we probably don't just want to test on nerds. So there is a bunch of learning from demonstration work on robotics where you just go down the hall, grab somebody else from a different robotics lab and have them teleoperate your robot. Turns out roboticists might interact with a robot differently than normal people. So I try to go out and focus more on, it's great to use subject matter experts, but let's also think about people who don't have a lot of domain expertise or machine learning expertise. But we just talked about action advice. Pascal already mentioned you could give demonstrations and use that, maybe use inverse reinforcement learning. You could also have people give feedback. So we know how to teach dogs, good dog, bad dog. You can teach good robot, bad robot. You can also show preferences. So there's some cool work, I believe it was OpenAI, where they taught a robot to flip by just showing people two trajectories, and the people chose the trajectory they liked better. And then over time, the agent was able to take those preferences and learn something cool. Right now, we're working a little bit on how to incorporate natural language processing. So having a human talking to the agent, trying to give it some advice. But for now, let's switch gears. Instead of talking about action advice, let's really focus on demonstrations. And a demonstration, so in general, you think of a demonstration as being you teleoperating a robot or you controlling an agent. You could also think of something like imitation learning, where an agent is watching a human perform the task. And maybe the human's actions are slightly different, or maybe the agent needs to figure out what actions the human was taking based on the states the human reaches. But for now, let's just assume it's a demonstration. The human can directly control the agent. So human agent transfer, the HAT algorithm. I always recommend try to come up with a cool acronym. In human agent transfer, we say we have a human demonstration. So the person is sitting down playing this game. You record a bunch of state action pairs. That's a trajectory. Oh, but wait, these trajectories, I could use this. This is just data. This is just a policy. So I can learn in a state, what action do I think the human would take? And then you can learn using supervised learning. You can learn a classifier. You could learn something that's human readable, bonus points. And then you could do something very simple. You could use, so Pascal mentioned you could use inverse reinforcement learning, get a reward, and then you could use that. If there's time, we can chat about that. A simpler thing you could do is just say normal RL trades off exploration with exploitation. Now we're going to have a third option, which is execute the action that I think the human's policy would be. So at the beginning, I'm basically going to just try to copy the human, essentially behavior cloning. And then over time, I can reduce this probability so that less and less, I am less and less reliant on the human, and instead am able to learn to outperform that human. So here's a concrete example. We see on right, we see keep away, and it's not a very hard game, but it's not trivial either. We actually have a different scenario where we speed up the simulator by a factor of 3, making it quite a bit more difficult, making the demonstrations worse, but the demonstrations are still much better than random, so they're still useful. In any case, the person's playing this game, we summarize those demonstrations, and then we use it, explore, exploit, or execute what we think is the human's action. So we do this, and voila, learning curve. One line is above the other. Awesome. Our line is in orange, and we improve the final performance. We improve the total reward. We look at the time to threshold. So how long did it take to get to a performance of 14? Well, it went from like 14 hours to 8 hours. Great. I can squint and these lines look really similar. Why do I care? Well, for a publication, it's statistically significant. So that's good enough. But is it actually significant? And this is one of the cases where we got these improvements with only 3 minutes of human training time. So in many domains, I would argue that getting a human to provide 3 minutes of training, if you can save hours, is often going to be worth it. If instead of episode duration, this had something to do with dollars saved, then it's even more compelling. But just like we saw with the action advice from a teacher, a student teacher, we can see that demonstrations, just a small amount of demonstration, can save a huge amount of time. And before I'm going to call for questions again in 2 more slides, but I just wanted to bring up, this was the HAT algorithm. And then we made the CHAT algorithm. So CHAT is confidence-based. So we did very similar to what we did before, but there was a question earlier about what happens when the teacher is imperfect and it has some confidence. So we could have a teacher which, for instance, has a neural network, and we look at the softmax layer. So with softmax, you've got one activation node for each action. And if it's really peaked, if the agent is really sure action 2 is the best, then it has high confidence. If the action activations were uniform, then the agent is very confused. So that's one estimate of confidence. And we tweaked the HAT algorithm so that we only execute if it's above some threshold. And that very simple modification, just saying only give the advice if you're really sure you know what's going on, that made, again, a statistically significant and actually significant improvement. So if the teacher, the demonstrator, has some idea of its own confidence or its own performance, you can absolutely leverage that and take advantage of it. Okay, so that was how we could use demonstrations. I want to emphasize that these are very simple methods. And since this, there are more work by much more, not just technically sound, but also complicated methods, which can outperform these simple methods. But I did want to emphasize these because, well, first of all, because I was an author. So, and if I'm going to talk about something, of course, I'm going to talk about myself. Sorry. But also just to show you how really that it can be easy to leverage this existing knowledge. If you've got it, you might as well use it. So now is another great time to pause and ask for questions.
Well, actually, I'd like to ask a question. Well, is there a feedback for the teachers' teaching performance, like to help it improve it, or where, you know, the best teaching has happened, things like that?
Yeah, that's a great question. So short answer is no, and there should be. If the teacher can learn how to teach better, that would absolutely be useful. And seeing that kind of feedback where it was giving good advice, where the advice was helping the most would be useful. Another thing I would argue is that when reinforcement learning is a black box, teaching is harder. So if you can look at your agent and Pac-Man says, I'm going down this hallway to run away from the ghost, versus Pac-Man goes down this hallway because it flipped a coin and that's the random action it took, that could influence how you teach. So I think there's a lot of really interesting human robot interaction, human computer interaction questions on how we could make better human teachers and how we could give humans better information so that they could teach more better, teach with higher confidence and achieve better results.
Thank you.
So I have a question as well. So here you are highlighting confidence as something that we can take into account to decide whether we take the suggestion or not. But isn't there also a question of, what if the confidence is inaccurate? I mean, with deep neural networks, we know that whenever we maximize likelihood, there's a natural incentive for the neural net to become overconfident, because according to its objective, it'll pay off to just be overconfident all the time. So here, is that an issue, or any suggestions about how to deal with this?
No, it's a great question, because we know, at least in America, it's something like 65% of drivers think they're better than average. So we know that people are not necessarily good at confidence. And you're right, neural networks and other function approximate or classification methods may or may not have accurately calibrated confidence. So if we have better statistically valid ways of calculating confidence, that would absolutely be more useful. But because the methods I've been talking about are mostly basically heuristic methods for leveraging existing agents, it's not really technically sound. That's fine. So the answer is yes, we should absolutely be worried about this, and we could absolutely improve things. But the tongue-in-cheek answer is, well, in practice, it hasn't been hurting us too much. But I do believe there's absolutely room for improvement there.
I think this is a really interesting point of discussion. Is there a way to regularize or somehow anneal that learning of, like, from a confidence type objective?
So one way I could interpret that is to say, initially, I'm going to take a lot of advice because I'm just bad. And then over time, I'm only going to take advice from the teacher when it's very confident. Is that what you were suggesting, or did I misinterpret it?
Yeah, I think I'm wondering. So there's the evolutionary strategies type unsupervised auxiliary reward, right? So like in regions of surprise, where you're predicting the next state, you may want to explore more. And I wonder if by knowing when your agent is not confident, will it rely on the confidence of some other agent more readily? And I wonder if there's a trade-off there that I think it's a delicate balance, but I think it could be really interesting.
Yeah, absolutely. Because if here I was talking about the teacher providing or deciding to listen to what we think the teacher would do. If I am not confident in what the teacher is predicting, maybe I downweight that. But if I, the student, have no idea what's going on, my confidence as a student could absolutely influence that. And if we could figure out, I don't really know what the teacher would do here. If I could figure out, actually, I think the teacher is garbage here, I need to learn my own thing. Or if I see something that's really weird, that could be a great time to ask the teacher for help because I don't know what's going on. Or it could be such a rare event, I'm pretty sure the teacher never saw that either. So I need to explore and figure out what the heck's going on.
Yeah. There's some interesting human interaction, sequential decision making, at least ideas out there. I'm not aware of any like completed papers about this, but where you have some decision support system out there that has access to historical data, and with that can make decisions quickly, but it will run into regions where it doesn't know. And so if you're working with a human expert, say a doctor or a stock trader, et cetera, it will say, hey, I have all this information about data that you don't have access to readily, but I'm in a situation where I don't know. What do you suggest, right? And I think that that could be a really interesting way to combine a lot of what has been discussed so far.
Well, and today I'm mostly talking about how can we make the RL agent succeed. Another related question is how can I make a human RL team succeed? Because there will be places where the human is absolutely better than any agent and vice versa. So you do not, at least at this point, you do not want an agent handling 911 calls. You want a human to do that. But if the human operator at that call center gets overwhelmed and there are some easy calls that an agent can handle, absolutely delegate those tasks and figure out what are the strengths and weaknesses. And part of that could absolutely have to do with different data sets and different confidences and novelty.
Yeah, great. Thank you.
Yeah, great question / idea. So let's see. I think, oh, wow, there's a real long one. Okay, so this is a paper I need to read from Graham. Awesome. Yes. So I'm just going to cut and paste this later. So I've covered about half of my slides, which is great. I didn't expect to get through them, but I've been giving talks for many, many years. I always get nervous. One of the ways I combat getting nervous is having enough backup content that I know I won't run out of stuff. So I'm going to skip a large section of the talk, but say that instead of giving demonstrations, you could also give feedback. So I mentioned earlier, you could say, good robot, bad robot. Well, we can learn from those. And I want to show this slide. Yes, because Pascal and Amir Masood asked me here, so I needed to put some math. I knew they'd be unhappy if I didn't have any equations. So here's one equation just to give you an idea that the trainer has some policy. So the human has a desired behavior, and I've got some history, and I can figure out what's the map hypothesis. What is it most likely that the human wants me to do? So you could think of human feedback as +1 or -1. You could also think of human feedback as categorical. And we were able to show that in some cases, this absolutely helps you. And the interesting thing here is, okay, you could have a prior over policies. You could also have the model of how the human trains. So you could say, well, if a human is training a dog, most of the time when you train dogs, you say good dog and you don't hit it. Turns out that's not good for dogs or children too. Whereas if you are grading an undergraduate's exam, some of us take a lot of joy in those big red X's. And, when they do something right, give them a little tick. So we posited there are different ways of training, that some people would give more positive feedback or more negative feedback. And we might be able to learn a little bit about what no feedback meant. Because a lot of the time, if the agent's going fast, you can't give feedback on every time step. So if I'm not saying something, am I not saying it because the agent's doing well? Or am I not saying it because the agent's doing poorly? And our experiments showed that different people do teach differently, and you can absolutely leverage that. So you can learn from feedback. This works in contextual bandits. This can work in MDPs. And this goes back to the earlier question about, can you train a person to teach? And we found that people do teach differently in this context, but I bet we could get those people to teach better. Or maybe over time, we could learn to better bias our agents towards how people teach or how one person teaches. But again, there's still a bunch of open questions here. One of them is, when is feedback better or worse than demonstrations. So for instance, I don't know how to fly a helicopter, but if I see a helicopter crash, I could say that's bad. Whereas a demonstration, if I can control the helicopter, then I have a ton of data. I have a long state action sequence, and I can probably learn more quickly from that if I have access to that. So we talked about action advice from an agent. We talked about learning from demonstrations from a human. I skipped over how a human could give feedback, good robot, bad robot. And I just want to briefly talk about just a few more ideas just to seed hopefully we have time for a little bit of conversation at the end. So one thing I did not talk about yet is existing data. If I have an agent, a person, a program that's been doing something, it absolutely makes sense to use that data. And we have off-policy batch learning algorithms that can do this. One of the questions we're looking at is, when do we want to switch over? When do we think our behavior policy, the target policy we're learning, is actually better than the behavior policy? What if I'm paying someone to generate this data for me? How does that influence when I switch over? How do we decide how much data we use towards learning the target policy versus evaluating the target policy so that I have a high confidence of when I can switch over? So that's one ongoing master's work. Another idea that we're working on now is that last piece. How do I help a human out? We have an RL agent. In this case, we're looking at an RL agent in a flight sim. And how can that RL agent be used to help pilots learn to fly more quickly? If I have one instructor with one pilot, which is what's normally done, that's not nearly as efficient if I have one instructor and 20 pilots flying virtually. If they can get some help from that agent, and the agent can also go and call in the human when needed. So this is absolutely related to intelligent tutoring systems, but looking at sequential decision processes. So those are a couple of ideas I just wanted to throw out there. So wrapping up, I'm going to argue that it's okay to cheat. If you've got existing data, existing programs, existing people, you should use it. Now, Rich Sutton argued in The Bitter Lesson that it's really better to spend our time on getting better algorithms. And I think for the 5 to 10 year outlook, that is right. We should absolutely be getting better algorithms. If I want to make our algorithms today work better, then it makes a lot of sense to use data, I believe, use that existing knowledge. And yes, we're absolutely biasing our agents. My argument is, as long as we can outperform the teacher, that's okay. But if you're really interested in minimizing your bias as much as possible, then using existing knowledge could absolutely point you in the wrong direction. But there's a ton of open questions here. One of the ones I'm particularly interested in is when one type of teaching is better than another. So that's in my submitted discovery grant, which hopefully I'll find out soon whether they liked it or not, and whether I get to spend 5 years working on that. So if you find this cool, if you found this interesting, I did teach interactive machine learning last fall. All of this information is and the entire class was online. So if you found this interesting, there's a bunch of papers and lectures by guest lectures and my own lectures on human RL and human ML interaction. And remember I said have good algorithm names? We have the Hippo Gym. So the human input parsing platform for OpenAI Gym. So if you are interested in running human subject experiments over the internet, we have a platform which is basically plug and play, where you can get demonstrations, you can get feedback, you can get mouse clicks for people interacting with Atari games or other OpenAI Gym environments over the internet. So if you're interested in that, please check it out. Please ping me. It's now public, and we're looking for more feedback from people outside of our own group to tell us what works and what doesn't, because I believe human RL interaction is really exciting, but programmatically it can kind of be a pain in the butt to get good experiments working over the web. So hopefully we can enable more research to happen more easily. So with that, we still have 5 minutes left for questions. So I would love to hear what other ideas or feedback or complaints you have.
Well, thank you, Matt. So big round of applause on behalf of the community. And yes, let's open this up to questions. So just feel free to turn on your microphone and then shout your question out to Matt. So do we have any questions from anyone?
Well, I have a question. So my lab works a lot on wireless networks, and we use a lot of reinforcement learning and transfer learning. And one of the problems for us is learning from rare events. So I was thinking whether this teacher learner approaches could be helpful in those, like a teacher experiencing a rare event, like a failure in the network, would eventually help a learner that would probably for a long time won't experience such a thing, but when it experiences, it has to act quickly. So what is your point of view on that?
Yeah, so I thought a little bit about rare events in terms of safety. And remember from Animal Farm, all animals are equal, some are more equal than others. All data is important, but some data is more important. And if you have those rare events and you have a way of recognizing them as rare, that could absolutely be something that a teacher hones in on. And hopefully, you're right, that if the agent experiences this rare event, hopefully it can recognize it and realize, I haven't seen this, or this is particularly dangerous. This is a great time to ask for help. Or even, I don't have an existing agent. This is a great time to hit the e-stop and tell the human something's going wrong. I need help right now. But I don't have anything super specific to say about that, other than I think that's a really interesting idea, and I'd be interested in talking more, because we, along with Pascal, we've been thinking about mean field reinforcement learning and thinking about how I can scale up to hundreds of agents, and wireless access points is one of those situations, especially where if you talk about cell phones, smartphones, and cell towers, and figuring out how to do RL, handling those important events, those rare events, is really interesting.
Thank you very much.
So Matt, I do have a question as well. So in terms of environments where we could experiment with this type of feedback and also having, let's say, software teach some software, have you considered the problems related to knowledge distillation and also neural architecture search? So here for knowledge distillation, we typically have a large deep neural network that will teach a smaller deep neural network to try to achieve similar accuracy. And then there's a whole literature on what type of information the teacher needs to give to the student and how best to guide the learning process. And here, this would be an instance of software teaching software. But then, there's a broader literature on also doing neural architecture search, and that's typically either done by humans purely or by software purely. And then we actually do use reinforcement learning for that. But in reality, it's probably best to look at this as like a hybrid thing. So any thoughts about that?
Yeah, so I'd never thought of neural architecture search as a combined human AI problem. I really like that framing, and I bet there's a lot of low-hanging fruit there. In terms of the knowledge distillation, so there, if you are you trying there, I think you're normally trying to make the network smaller, but also to help it generalize better. Is that right?
Yes.
Okay. Yeah. So that would be a great place if it's the same task. That's even easier. So it's not really transfer learning, but you could think of teaching or transferring to a smaller area. That sounds like a great place where some of these methods could be used. But that was a long way of saying, no, I haven't thought specifically about that. It's a really good idea.
Okay, good.
Hey, Matthew. Thanks for the talk, and thanks for the fall course last year. It was pretty interesting. Just a question in terms of teaching. So, for example, if we're working with systems where the advice usually comes in a delay manner or in a very vague manner. For example, when we work with human-robot interaction, where the advice is usually after the whole training session, or for example, when we are talking about rehabilitation robotics. So the advice usually is really vague and it doesn't pinpoint to a specific action state pairs. And how do you have any advice in terms of dealing with those like long-term abstract and vague suggestions?
Yeah, so I think there's at least two really interesting questions there. One of them is the temporal delay. So if a person is just watching an agent and hitting the good agent button and hitting the bad agent button, they are not perfect. So they're going to be delayed. And you could try to estimate that delay, maybe put a Gaussian over it. But if it's someone going back and just saying, oh, by the way, 5 minutes ago, you messed up, that's going to be kind of hard. One of the things we've looked at is having a person look at a video and drag forward and backward in time and say exactly where the error was made. So that helps. In terms of the imperfect or vague advice, that's another level of hurt. So if the person just says, yeah, that was definitely a thing. What is that? Does that mean I did well? Did it do poorly? Does that mean I shouldn't have touched that button? So I think depending on how vague or imperfect the advice is, you should be able to use it somehow, but the less specific it is, I think the less valuable it's going to be. So the more you can force the participant to give you the kind of high quality advice you can use, the better. But even if it's not great advice, as long as it's better than random, hopefully it's still useful. That sounds like a really difficult but very interesting challenge.
Yeah, that totally makes sense. It seems like by having the advice in a binary manner, so either yes or no, it may sort of get rid of some of those uncertainties if we don't have an understanding of the actual level of the advice. Thank you.
Yeah, you're welcome. And just a quick note, in all of these human computer interaction things, a big part of this depends on the human's understanding of the task. So if they are not a robotics expert, if they don't understand the task, if they don't understand machine learning, you can still probably get good information out of them, but it becomes a different challenge.
Okay, so I think we've reached the end of the hour. But I guess so if anybody needs to go, by all means, feel free to go. If Matt is still available, perhaps we can take a few more questions, and if not, I guess we can also end it here. But I'll just give a chance again for anyone else to ask questions. Okay, it looks like there are two hands raised, so I don't see those hands raised at the moment, but whoever that is, please turn on your mic and go ahead.
Sure. I guess I have one quick question. Are there kind of work on multi-agent setting? Not in the sense of like we have only 2 agents, but like say we have hundreds of agents learning something together, like somehow like living in a society, but then learning basically to give advice to every other one in the same society in some sense, like massively multi-agent systems.
Yeah, so what I focused on today was saying I've got a teacher and a student. For instance, Felipe Leno da Silva has his PhD focused much more on how do I have a group of agents that are working together and sharing knowledge. So it's similar. You can figure out when one person needs help, when one agent needs help. You can figure out when one agent might know something more than another one. You can figure out how useful that advice would be. But now there's this extra level of uncertainty because as the agents are learning, many of them are likely confused. Many of them are very suboptimal. How do we use this even less perfect knowledge? But you're right that there are absolutely situations where I do not have a trained agent, do not have a trained human. If I've got a multi-agent system and they are at least somewhat cooperative, why not share that knowledge? You know, if it's a competitive setting where it's a death match and all the agents are trying to kill each other, they're probably not going to help each other out so much. But there are absolutely many settings where these agents should be collaborating and sharing knowledge and sharing parameters.
Okay, so now I do see the raised hand. So Yudong has his hand raised. So Yudong, please go ahead.
Yeah, hi, Matthew. Nice to meet you. Yeah, I relatively have a detailed question about one paper you mentioned in your slides. So the paper named the uncertainty while action advising for deep reinforcement learning. Yeah, I think for the uncertainty, as you mentioned in your paper, there are generally two kinds of uncertainties. One is epistemic uncertainty, and another is the inner uncertainty of the environment. And I think in this paper, you like instead of learning a scalar value for Q values, you instead you use many hide to output several samples for Q values for state and action pairs. So my question is, why you think the variance of these Q value samples only represent the uncertainty of the epistemic uncertainty? Why is not the summation of all the uncertainty, like including the epistemic uncertainty and the environment uncertainty?
Yeah, so that's a great question. I think I want to take one step back and say there's probably actually three kinds of uncertainty now that I learned about after this paper. So there's one kind of uncertainty, the environment is noisy. I can know exactly what a coin is, but I still only have a 50-50 chance of guessing whether it's heads or tails. There's also the uncertainty while I'm learning. I don't know how good this coin is, so I just have to guess. As I get more data, I have a better estimate of that coin. A third kind of uncertainty that this paper didn't address at all was, is my function approximator strong enough to learn the correct hypothesis? So there could be some error or some uncertainty because it's not powerful enough to really represent the true value function. So here, what we were trying to do is say, well, let's try to estimate that head. Let's go back to say I'm just trying to estimate the heads or tails. If I have a bunch of predictions and they are all over the place, I probably don't know what's going on. If, because Q values represent the expected value, the average value, if many of these guesses have converged to 0.5, then I've got pretty high certainty that my different Q values know what's going on. And in expectation, I'm going to get 0.5, and I'm just not going to be able to tell you on any given coin flip, is it 0 or 1? So in the paper, we tried to argue that we were addressing that one kind of uncertainty, but I believe there's a lot of interesting work that could absolutely be done on better understanding these different kinds of uncertainties. And this does also go back to the value of information, because if I say, I don't know whether this coin is going to be heads or tails, it doesn't help if I try to pay someone to tell me that the coin is perfectly balanced. That's not going to help me predict whether the next one is heads or tails. Or if it's an oracle and they can look into the future and say, oh, it's going to be heads. Well, I just learned about that one next coin flip. I didn't learn anything that's going to help me in the long term. Or it's still going to just be, I've got a 50-50 chance. It's not going to tell me whether it's heads or tails 2 flips from now. So that was kind of a long-winded response. Did that address the question you asked, or did I kind of avoid the question you really asked?
Well, so if the environment exists some random or randomness, it will also lead to the variance of the Q value samples to be pretty high. So
Right.
if you only look at the variance of the Q value samples, it will not only represent the epistemic uncertainty. I think it's also include the environment uncertainty.
Yeah, and I think what we were trying to argue was that over time, your Q values should all converge to 0.5, even if you're getting zeros and ones. If these Q values were not able to converge, if they did not agree on the same expected return, then I think I would agree with what you're saying. In practice, we found that they did converge.
Oh, okay, I see. Thanks.
Cool, thanks for the question. And it sounds like you read the paper, so
Yeah.
Double thanks for that.
Okay, very good. We also have a hand raised from Mileki. So if you'd like to go ahead and ask your question.
Yeah, sure. Well, first of all, I think I forgot to say at the very beginning, an excellent presentation. So that's why I think you're getting a lot of questions on that. And I was wondering something about what Pascal had asked before about the cost of teaching. And in your problems, is it of a concern whether the cost of communication, like for teaching, basically the agents will need to communicate, the cost of communication, plus if there is some problems in communication, like the impact of late feedbacks?
So can you ask your question again?
So yeah, yeah, I probably left it out like a comment. So the yeah, the question is what would be the impact of a late feedback, like an obsolete or stale feedback of a teacher?
I see.
And
Sorry. Yeah.
yeah, like if there is too much communication between the agents for teaching, would that be a problem in these tasks?
Yeah. So in the real world version, if you had a bunch of agents that are doing real communication, you would absolutely need to worry about latency. You'd need to worry about dropped packets. You need to worry about noise. And I think all of that could go into it. If you're able to give this feedback with a timestamp, hopefully that will alleviate a lot of this, because in general, the agent shouldn't only be able to say, tell me what action to take. Okay, I'll execute it. Because that you need real time, and you can't go on until you get that information. In general, in the real setting, you should be able to grab information from a teacher about something you did an arbitrarily long time ago, go back in time and use that information to update something, so that when you get near that state again, you make a different or better decision. But the simple, oh, I'll just wait for the teacher to tell me what action to execute, that's not going to work very well if you've got large delays.
Perfect, thank you.
Okay, very good. Are there any other questions? So let's wait a few more seconds. So yeah, if anybody has a question, so Matt is here and happy to take some more.
I think I'm actually going to cut it off now, since I'm
Okay.
12 minutes late for my next meeting. But I already apologized on Slack, so it's okay. But Pascal and Amir Masood, thank you so much for inviting me. Like I said before, it's great to visit Ontario again. And maybe one day I'll even be able to see you in person, where in person doesn't mean looking at a screen.
Yeah, that would be wonderful.
Yes. Okay, thank you very much. See you.
Awesome. Thank you so much, everyone. I really appreciate the questions.